In this video, I would like to give you an introduction to T-distribution. So in the previous lesson, we discussed normal distribution, we discussed the Z procedure, we discussed central limit theorem. So what happened was we have a normal distribution. So do you see that there is a bell curve and then the mean is right in the middle, and then I am taking samples from this population. So N1 is my first sample, N2 is my second sample, N3 is my third sample, so on and so forth. So I have many samples, and then for each sample I have a corresponding sample mean. So x1 bar is the sample mean of the first sample, x2 bar is the sample mean of the second sample, so on and so forth. Now what I am asking is, you have a bunch of x bar, right? What is the distribution of this x bar? So the distribution of this bunch of x bar is called the sampling distribution. So the sampling distribution of this x bar, not just one x bar, many x bar. So the distribution of this a bunch of x bar is normal with mean equals to mu and standard error sigma equals to square root of divided by square root of n. So when you standardize, you have z equals to x bar minus mu divided by sigma over square root of n. So in that green formula, do you see that I use a red color to write sigma? Now that leads me to another question. That question is how we start T-distribution. Now what happens if sigma is unknown? If sigma is unknown, are you still able to calculate z? The answer is no. So listen to me. When sigma is unknown, we are not able to complete the standardization process. That means you are not able to calculate the z value or z score, whatever you like to call. So in this case, when sigma is unknown, listen, you have to use T-distribution, or you can call this a T procedure. So for the Z procedure, the normal distribution, do you still remember that there is a very complicated PDF for the normal distribution and you don't really remember what the function is, right? So don't worry about that, because in T-distribution, we have a even more complicated probability distribution function. So take a look at line 3. So the probability distribution function of the T distribution is f of t equals to a bunch of stuff on the right hand side of the equal, right? So don't worry about it. I know the function is very complicated. Don't worry about this. So listen to me. T is a random variable, and then the V is degree of freedom. So degree of freedom, we just call it a DF for short. D stands for degree, and then F stands for freedom. Degree of freedom is easy. You just have to take the sample size minus 1. So in this probability distribution function, T is a random variable, and the degree of freedom is a parameter. Again, T is a random variable. The degree of freedom is a parameter. Why do we call the degree of freedom a parameter? Because, this is extremely important, because the degree of freedom controls the shape of the curve. All right, back to the normal distribution, the mu and sigma, they control the center and the spread, right? For T-distribution, the degree of freedom determines the shape of the T curve, right? So degree of freedom came from sample size minus 1. So therefore, when you do T-distribution, the sample size matters, because the sample size gives you degree of freedom. The degree of freedom determines the shape. What shape? Look at the graph I gave you. So I have 3 curves, right? One in yellow, one in red, and then one in blue. So the one in yellow, that is a T-distribution. So let's just call that a T curve, shall we? So we will just call this a T curve for short. So the T curve, let's take a look at the yellow T curve. So the yellow T curve is the curve of T-distribution when the sample size is small. So when the sample size is small, so basically you don't really see a bell curve, right? That looks more like a semicircle to me. So when n is very small, we have something that looks like a semicircle. So what if you increase the sample size a little bit? So if you increase the sample size, that means you increase the degree of freedom a little bit. So the degree of freedom changes the shape of the t curve. So the next curve that you have to look at is the red curve. So the red curve is t-distribution when n is close to 30. So when n is getting closer and closer to 30, we can see that the t curve is actually pretty similar to the normal curve, right? What if we make the t even bigger? So if you make the t even bigger, the t curve is just look like, not exactly the same, it's just look like the standard normal curve. Again, when t is very small, how small is small? Less than 30. You see something like a semicircle. It doesn't really look like a bell curve. When t is close to 30, the t curve is similar to the z curve. So the z curve, so I'm going to write one more word for you, the z curve means normal. T is t-distribution. If you make the sample size a little bigger than 30, the t curve is very similar to the z curve. All right. So overall, the shape of t-distribution, I cannot just give you a bell curve because the shape changes depending on the parameter. So on the blue handwriting, you see that the shape is determined by the degree of freedom, n-1, so the sample size matters when you use t-distribution. The sample size is everything because that determines the shape of the t-curve. So the t-curve is similar to the z-curve, just let n equal close to 30, the bigger is better. So let me give you a big picture of the t-distribution. So why do we use t-distribution? When sigma is unknown, you are not able to do z anymore, right? You cannot standardize because if sigma is unknown, there is an unknown quantity in the formula, then you cannot find the z. All right, so all we have to do is we consider t-distribution. So when you consider t-distribution, you have to replace the sigma. What sigma? Let me remind you this standardization formula. Z equals to x bar minus mu divided by that sigma over square root of n. So you don't know that sigma, don't worry about that. We consider t-distribution and then we replace that sigma with sample standard deviation because sample is an estimation of population, right? So the number that is closest to the sigma is sample standard deviation, which is the lowercase s. And then we use another standardization formula, which is t equals to x bar minus mu divided by s over square root of n. So that is another standardization formula that we will have to use in t-distribution, or you can call it a t-procedure. So as long as n is greater than or equal to 30, the result is similar to the z-curve. So here, when the sample size is large, then you have a big degree of freedom. The degree of freedom is equals to n-1. So large n gives you a large degree of freedom, then the result of using t-distribution is very similar to the result of using a normal distribution. So overall, you lose sigma. Don't worry about it. Just replace the sigma with sample standard deviation, and then we use another standardization formula. As long as the n is big enough, the result of using t is very similar to the result of using z, right? And then, so that will be the end of this video. So if you think my instruction is helpful, let me know in the comment section below. Like the video, subscribe to my channel, share the video for me. Appreciate your help as always. But before we close this video, do you see that I use the word degree of freedom in this video? So degree of freedom comes with a very complicated definition. And then to explain degree of freedom, I will start another video. So in the next video, the one follow this, I will show you why the degree of freedom is n-1. All right, so I will see you all in there. Signing off for now.